In this video, I'll be covering chapter 5 for atesin lecture. I haven't done chapter 6 yet, but I'll probably do a video on that tonight or tomorrow morning. And my bad that this video is pretty late. Chapter 5, in my opinion, is the hardest chapter out of all the chapters we learned in this semester so far. So it took me a lot more time than I thought it would. And these notes here and the practice exam and the POTO questions are the only three things I use to study for the exam. I've personally never used RealChem before. And these notes will be on the WhatsApp message. And I spent a while on these notes, so what you have in your own notes should also be in these notes. So you don't have to keep checking if I'm missing anything. And what I'll say in the lecture will all be typed on the notes itself, so you don't have to take any additional notes. And also I highlighted these notes just to show, like, this is a topic, this is a topic, and this is a topic, so it's more organized and it's less of a mess. So the Bronsted-Lowry definition of an acid is a compound that donates an H ion to another compound, and the base accepts an H ion from another compound. So in this example, HCO becomes CO, HCO becomes H3O plus. This is a pair, and this is a pair. And when HCl becomes an CO minus, it loses an H plus. So that means it donates an H plus, so it's an acid. And acids become conjugate base, and bases become conjugate acid. So don't pair these two together. And H2O plus becomes H3O, wait, H2O becomes H3O plus, so it gained an H plus. So this is a base and this is its conjugate acid. This is just another example. And we have two definitions here. First one, this is just a species that can accept or donate a proton, like water, which can be an acid or a base. And the second definition here, the auto-ionization in water is just that water does an equilibrium reaction with itself. And next are these equations on the equation sheet. So I kind of just organized them in a different way. This and this, so these two are kind of the same equation, just written in P form. This one is just written in the P form, this one. So the P is just a negative log of something, as shown here. So yeah, it's just a way I organize it. And these two are also the same thing, just written in a different way. And also H plus and H3O plus is used interchangeably, so it's kind of the same thing as well. And in this equation, if, just an example, if POH is 5, then pH will be 9. So if the pH of one goes up, for example, not the pH of one, but if one goes up, the other one goes down. So if this was, instead of being 9, if it was 12, this would be 2. And same thing here. If one goes up, the other one goes down. This is what this here says. So it's just a relationship that you should know. And also we learned this from last chapter. The brackets just mean it's a molarity. So what you should put in the brackets should be in the units M, capital M. This here, you probably already know that acids are from 1 to 6. Bases are from 8 to 14. And 7 is neutral. This just shows that because of the p function, when this when the molarity goes down, when the molarity decreases, the pH increases. So just be aware of how that's written. That's what this is. And acids and bases will always exist together. For example, in these two, for example, if we have an acid, then we have a base. And even if there's an acidic solution, that means that there's a large amount of acids and a small amount of bases. So there's acids and bases will always exist together. Even in the most acidic solution, that just means that there's only a tiny amount of bases, and vice versa. So there will never be a scenario when an acid is 0 or a base is 0. You probably already know that H3O plus is an acid and OH minus is a base. This here just says that when there's more in a solution, when there's more H3O plus than OH minus, then it's an acidic solution. When there's less H3O plus than OH minus, it's a basic solution. And when they're equal, it's a neutral solution. So now I'm going to talk about strong acids versus weak acids. So all of this is talking about that. In lecture, he told us to memorize these 6 strong acids by heart and these 6 strong bases by heart. And any other acid that shows up in questions that isn't here will be weak, or we can consider them as weak. And any other base that shows up that isn't these 6, we can also consider as weak. And so now this is just talking about this relationship between strong acids and bases and weak acids and bases. So strong acids and bases have a one-way reaction. So all the reactants will dissociate into these products. All the reactants will dissociate into products. So it's not an equilibrium reaction. So none of this will form into this. There's no reverse reaction. And for weak acids and bases, there is an equilibrium reaction. So some of these will produce these basically. So since there's a reverse reaction in weak acids and bases, there will always be some reactants and there will also be some products. So basically what I just said about this is strong acids are a one-way reaction, weak acids are an equilibrium reaction. Now for this part of the notes, it's talking about the calculation part, the calculation difference between strong acids and bases and weak acids and bases. So for strong acids and bases, we do ratios of coefficients to find pH. So in this example, we know it's the coefficient in front of each compound is 1. So it's 1 molarity of HCl, or 1 mole of HCl plus 1 mole of HCl to 1 mole of HCl plus and 1 mole of Cl minus. And so we also know that the ratio of molarity is 1 to 1, since it's all 1 to 1. So if the question says that we have 0.1 molarity of HCl, then that means we'll make 1 molarity of H3O plus. And if we use the formula we learned from here, pH equals negative log of H plus. So pH equals the negative log of that, which is 0.1 molarity. We can put this in the calculator and find that it's equal to 1. And the same thing applies to finding pH for strong bases. We do the same thing. Look at the ratio of the coefficients. And right here, the coefficient is 2. So if the question says that we have 0.1 molarity of this, then we'll have 0.2 molarity of this. And the only difference here than here is that we'll find POH instead of pH. So we found that POH is 0.7. And most questions will ask for pH. So we just use this formula to convert pH. To convert POH to pH, which is what's done here. So what I just said here is the calculate. Wait. Okay. What I just said here is a calculation for strong acids and bases. And again, how do we know if it's a strong acid and base or if it's a weak acid and base? One way to know is we can look at if it's a one-way reaction or equilibrium reaction. But if the question is an equilibrium reaction, so if it's asking for us to find the pH of weak acids and bases, we do ice tables. And these are two tools we can use for ice tables. This formula and this formula. I'll briefly go over these and I'll come back to it and use them in 2 ice table questions I'm going to do below. So you probably learned this formula in the last chapter or the last second to last chapter. Which is finding the K value of something. And we need to find the K value first for weak acids and bases in order to find pH of something. So to do K values, we do the products that are aqueous or gases. We probably won't use gases at all in this exam, so don't worry about this. So it's the aqueous reactants over the aqueous, wait, my. It's the aqueous products over the aqueous reactants. So for this equation, for example, it'll be these two over that. For this example, it'll be these two over that. The only difference between these two is for this one, we're finding the K value for acids. For this one, we're finding the K value for bases. So just know that if a question, let's say for the table questions, we'll do it in a second. If it's saying Ka is equal to something, this K, we know it's the K value for the weak acid. That's just what these say. And remember again, we only include aqueous solutions or aqueous species in the equation. So water isn't included. So right here and right here, you'll see that water isn't included because it's a liquid and not an aqueous species. That's why I crossed the B off, just for a reminder. So we just covered this formula over here. Now we're gonna cover another formula we can use to help us find the answer when we do ice tables. Is this formula. Ka multiplied by Kb equals to Kw. And this formula is on your equation sheet. Right here. And this is equal to that. And one thing to be cautious of, these have to be conjugates of each other. So we can't use a random weak acid and a random weak base in the formula. We have to use the weak acid and the conjugate weak base of that weak acid, and vice versa. So example, in that if HF is a weak acid, then we have to use F for the weak base. We can't just use another weak base. That's just what this is. And you'll see that pattern. We'll use that pattern when we do ice tables. So we just covered the relationship, the calculations, their difference in calculations. And before we do ice tables, I also want to teach. It's kind of or he taught this concept kind of separate from these, from weak acids and bases, but I'm going to teach them together because you need to consider them when you do ice tables. So this is saying when you dissolve a strong acid or base in water, it will not cause a pH change. So it will make the solution more acidic or basic. And opposite of that, when you dissolve a weak acid or base in water, it will cause a pH change, making the solution more acidic or basic. I should have organized this a different way. So this is an example of a strong acid and water. The water is included here in the equation, but it's showing that, or first of all, this is a salt and this is a salt. Salts dissociate. For example, you probably remember NaCl is a salt, and it turns into when it's in water, it dissociates into Na plus and Co minus. So this is a salt here. It dissociates into Na plus and NO3 minus. Same thing with, let me add, okay, I just added the equation for the dissociation of NaF. So again, this salt dissociates into, and you probably remember that cations are something plus and anions are something minus. So this salt dissociates into this cation and this anion. And this salt dissociates into this cation and this anion. Now, how do we know if it's a strong acid? How do we know if it's the cation or anion of a strong acid base or a weak acid or base? We know that from this. We know that because of the list of cations of strong bases and the list of anions of strong acids. That you should remember. You should memorize by heart for the exam as well. But you don't have to memorize these separately. Because up here, you were told to memorize these strong acids and strong bases. And these are derived from here. These are derived from here. So for the exam, you just need to memorize these 12 things, and then you can derive the cations of strong bases and anions of strong acids from those. So you don't have to memorize these separately. So how we know if it's an anion or cation of a strong acid or base or a weak acid or base is from this list. And in this equation, we can see Na plus is here and NO3 minus is here on the list. So, and remember what we said about cations and anions of strong acids and bases. It won't cause a pH change. So, if we dissolve this salt in water, the pH of the water will stay the same. But here, in this dissociation, Na plus is again a cation of a strong base. So Na plus here won't cause a pH change in water when it's dissociated in it. But F here, F minus here, isn't on this list. So F minus will cause a pH change in water. And what's F minus? And is it an acid or a base? It's a base, like OH minus and other bases. So since it's a base, it will make the water more basic. So when we dissolve the salt in water, the water will become more basic. Since F minus is a anion of a weak acid base. Hopefully I explained this part well and it's not too confusing. One more thing I want to add, this part, you don't really need to memorize it. Because you know cations are something plus, right? And H3O plus is also something plus. So an H3O plus is also a cation. And you know H3O plus makes a solution more acidic. So that's just a way you can know that cations make solutions more acidic because H3O plus is also a cation. That way you don't need to memorize this. So next I'll be doing two ice table questions with you using everything we just learned here. Yeah. And right here, I put 4 steps you should take when you do ice tables. And I'll do these steps with you or explain them while doing the ice tables. Okay, split screen, so the steps are on the left and I'm going to do the calculations on the right here. Before step 1, remember, ice tables are for using, or we use ice tables for weak acids and bases. So we don't use ice tables for strong acids and bases. So once we identified it's a weak acid and base, and we're using ice tables, then we can start doing these steps. So this right here is, I just put it here basically. So for this question, we do step 1, which is to write the equation. And acid-base reactions are always something with water. So it's what will we have for the reactants? It would be this and water. And we will produce H3O plus or OH minus in the products. You can see here as well, in these two equations we've been through, it's something plus water and then turn to H3O plus or OH minus and the conjugate of that. So I'm gonna write the equation, which is that this and water to one of these and that. And we know it makes H3O plus and not OH minus because the H here, there's an H plus here that combines with this kind of. And step one, in writing during writing the equation, we check if there's an anion or cation of a strong acid or base in the reactants. Do we? Is H plus a anion? Where is H plus a cation of a strong acid or base? How do we know that? From the list we had over here. And H plus isn't on the list of cations of strong bases, so it's not a strong, where it's not a cation of a strong acid base, so we don't do this dissociation thing. So we're done with step one, we wrote the equation. Step two, this is just to make sure, are we finding the pH of an acid or a base? We are finding the pH of an acid. How do we know that? Because this donates an H plus to water. So just label, we're finding, or if we're finding the pH of acid, we use Ka. So we use Ka. And is this going to find pH or pOH? It's going to find pH when we do the calculations, because it's acid. This is just to keep in mind of. I'll put this here. So now I kind of edited this. So we're using Ka, and after we do our calculations, we're gonna find pH. So now we're done with the first and second step. We're doing the third step, which is making the ice table. And just a little review of ice tables. Oops. Just an example of an ice table here. This isn't applied to this question. It's just an example. We set up the table under our equation, and make sure that what we put here in this column is in molarity. not moles, not other units. It's in molarity. C, this row, we put something X, and the E row, we add these together to form that. That's just a review, little review. So, okay, I shifted the equation here more to the center and also added the ice table. So, for I, we put the molarity that we're given. But we're not given any molarity here. So, to get that, we remember molarity, the units for molarity is mole over liters, right? So, I think I also put here, wait, never mind. I think it's down here that I put the equation. But using the units for molarity, you can also know or get the equation. So we know molarity is equal to mole over liters. So for here, it's moles over liters, which is equal to 1 m, or just 1. Wait, oops, 0.1 m. And remember, all the way somewhere up here, I said for, yeah, up here for ice tables, we only use aqueous, right? So we don't use water here. So I should probably include in the steps. Oh yeah, I did. Okay. So excluding water. So you should cross out water, just as a reminder that you will not be using it. Because when you, later on, when you do this equation, you won't be using it as well. So I'll cross it out. And H3, in this question, it doesn't state if there's any H3O or H3O plus or C2H3O2 minus. So this is 0 and this is 0. And now for the C row, we put x's. And to know if we put a positive x or negative x, we see if it's a forward direction or a reverse direction. So is it a forward or a reverse direction? We know it's a forward direction because we have an amount of this, but we have none of this. So the reaction will be going to the right, going forward to the right, which means we'll be gaining this and this, and we'll be losing this. So This will be negative x. This will be positive x. And this will also be positive x. Now for e, we just add these. So it's 0.1 minus x, or plus negative x. And this will be x, and this will be x. Now we're done with the ice tables. Now we find pH. And we can find pH using the two tools I wrote here. Two tools. This equation and this equation. So I should probably write using the two tools. And I should probably also add that I added these two things. You should first try using this equation, then you should try using this equation. So, can we use this equation? Well, let's plug in everything first. So, let's go back here to our question. And we can write this. Because it's the reactants, or it's the products over the reactants, excluding water because it's a liquid. So next step is just to plug everything in terms of x. So like this. Ka, we know Ka from here, and H3O is x. That is also x, and that is that. So it's x times x over 0.1 minus x, which can also be written as this. And a rule for these type of ice tables is that if there's a minus x or plus x in the calculation, you can ignore it basically. So I don't think, just two examples. Right here, this x can be ignored and this x can be ignored, but this x can't be ignored, and this either of these x's can't be ignored because it's multiplied. This is just to save time on your ice table calculations. So now that we ignored x, we can then rewrite this as this. And then we can then find x I'll just copy all the work. So we've done this step, this step, this step, and then we just do math and then find x, which is equal to 1.3 times 10 to the negative 3 molarity. And we're not done yet. We found x, but not the pH. And remember, we're finding, we using this, after all these calculations, we're finding pH. So we use the formula for pH. So if we look up here, pH, we use that formula. For this. So we put this number into that. Like this. So that's basically it. We found the pH for this, which is 2.87. Now for the second istable example, you do the same thing. Write the equation first. And this time, there is an anion or cation of a strong base, strong acid or base in the reactants. How do we know that? We go to our list, and Na plus is a cation of a strong base. So we do dissociation of this. And we do it basically like this. So we had 1 mole of sodium acetate, and we dissociate into Na plus and C2H3O2 minus. And because the coefficient is 1, so the ratio of this and this is also 1:1. So if there's 1 molarity of this, then there's 1 molarity of this. So with this, now we know we have 1 molarity of this, and we do the same thing where we write the equation, and then well, let's see if we're okay. So we first write the equation, which is this. That plus water, because it's always something with water, equilibrium reaction to that and that. And so we're done with the first step. Second step, do we use Ka or Kb? Is this, or are we finding the pH of a acid or base? We're finding the pH of a base, because this accepts a proton from water. So we're finding the pH of a base. So that means we're using Kb. And that means we're finding pOH, or the calculations will make us find pOH. So, like that. So now we're done with the second step. We know we use Kb and we find pOH. So now third step, we make an ice table, and same thing. We have, this is the ice table already done. We have 1 molarity of that and nothing here. So it'll be a forward direction. So it's minus x. Same thing as the previous question. Now after we're done with this third step, now we find pH. Again, using the 2 tools we have over here. We first try to use this. So it's going to be like that. Because it's reactants, it's products over reactants. And we know we're using Kb. We wrote in step 2. So then we can do the same thing and plug it in. Plug in this and this here, that here, and ignore the minus x because of the rule. But we don't know Kb. We need Kb, but we don't know Kb. So now we use our second tool here. This formula to find Ka. And we know Kb, to find Kb. And we know Ka is this, and Kw equals to this. So using that, we can rearrange this equation to Kb equals Kw over Ka. So we can rearrange this to that. and then plug in the values. And then now we know that's equal to KB. And we equal this to that, do some more calculations to find x is equal to that. So now we have x, and the next step we do is to find POH. Remember, we wrote we'll find POH in our calculations right here as a reminder. So next step, you calculate POH like that. And now there's an extra step because the question's asking for pH. So you gotta convert that to the POH to pH simply using this formula, like that. So that's how you do the second istable question example. So again, if it's a strong acid or base, we do this. We don't do any K stuff for strong acids and bases. And for weak acid and bases, we do istables using these two, and we can use these two tools. So yeah, that's basically it for that part. And this is just a simple relationship. As Ka, as the value of K gets larger, the acid gets stronger. And as Kb gets larger, the base gets stronger. So a question can ask, in these two reactions, which is stronger? And the answer would be this, because that's more than that. So now we do another topic on definitions, on these two definitions. Monoproduct means monoproduct is an acid that has one ionizable hydrogen atom, like that. And polyproduct means it has more than one. So that's polyproduct, and that's polyproduct. And these two are monoproduct. And this isn't an acid, so it's neither. And you determine this by seeing how many protons it can donate, not how much H there is in total. So for this, for example, it's monoproduct because it can only donate one H. And it can't donate these three H's. And polyproduct acids donate their protons one at a time in steps. So it donates one H to water, forming that, and then this donates another H to water, forming that, and then that donates another H to water, forming that. And so it donates its protons 3 times. And for all polyprotic acids, the first proton will be strongest and have the highest Ka value. Remember, highest Ka value means it's the strongest, or larger Ka value means the acid's stronger. And the ones after that will be weaker and weaker. So that's it for this part. The first one will be the strongest, and the last one will be the weakest. Now another topic, buffers. Buffer is a solution that keeps the pH stable around a specific value even if external acids and bases are added to the solution. They're formed by mixing a weak acid and its conjugate base, weak base. So when it works, because when an external base is added, the weak acid in the buffer neutralizes that. And when an external acid is added to the buffer, the conjugate weak base of the buffer neutralizes that external acid. And this is kind of just another way to describe it in a more specific way. The pH of a solution with a buffer in it can still change. Will still change when an external acid and base is added to it, but it won't change much because the buffer will keep it stable. All buffers have a buffer capacity because there's only so much weak acid and conjugate weak base in the buffer. So if we add too much base to the buffer, all of that weak acid will be used up and the buffer runs out and doesn't work anymore. Vice versa too, if you add too much external acid to the solution with the buffer, all the weak base will be used up. And so there's no more buffer. So pH won't be regulated anymore. So pH will start changing a lot. And this capacity depends on how much weak acid and its conjugate weak base there is in the buffer. So if a buffer only has a little bit of weak acid and a little bit of its conjugate weak base, if we add external acids and bases to it, it will quickly be used up. But if there's a lot of if there's a lot of buffer, there's a lot of weak acids and a lot of conjugate weak bases in the buffer. If we add external acids and bases to it, it won't be used up as quickly. So there's a higher buffer capacity. And this capacity can be written in a range of plus and minus 1. So it's better to explain this with an example. So if the pKa of this acid is 3.8, its usable range is 2.8 to 4.8. So plus minus 1 and plus 1 of 3.8. Same thing here. And if we want to use a buffer for a solution, we want a buffer that's closest to a buffer with a pH range that's closest to the pH of the solution. So if we have a solution with a pH of 4, we would use out of this acid and this acid, we would use this acid because the range is from 2.8 to 4.8. It's closer to that. We're 3.8 is closer to 4 than 3.1 basically. And to calculate the pH of a buffer, we use this equation called the Henderson-Hasselbalch equation. So this is just an example of how to plug in. If this is the equation, then if this is the chemical equation, then this will be how it will be plugged in. The conjugate base over the weak acid. So the conjugate base of the weak acid and the weak acid itself. Now for the second to last thing for this chapter is on acid-base titrations, they're also called neutralization reactions, because if you remember from Gen Chem 1, neutralization reactions produce water. So these are two examples, just showing that just shows that it's reactants, and then it forms reactants with NaOH, so, sometimes with NaOH, but not always. But neutralizations always produce water and a salt. Water and a salt. So, and all acid-base titrations are exothermic reactions, are all instantaneous reactions, all produce water and salt as a product, all are one-way reactions, not equilibrium reactions. So all of them look like this with arrow in one way, then equilibrium. And remember that in any acid-base titration, use liters for volume when you do the calculations. So convert, if you are given a volume in milliliters, then convert that to liters. And a definition, equivalence point. This definition Equivalence point means the point during the titration when the amount of acid equals the moles of acid equals moles of base. So when it's a point when the amount of acids and bases are equal. And remember just to keep this formula in mind, and and just stands for moles. So there's two types of acid-base titrations: a strong acid with a strong base, and a weak acid and a strong base. First of all, what does these mean? You probably remember in Gen Chem 1 lab, you did titration lab where you use a long thing to to drop drops into a beaker below. This just means that you have a strong base in the beaker and you're adding a strong acid from the long dropper thing, which is called a burette, I think. And you're adding the strong acid to the beaker with the strong base. And same thing here, it's just you're adding a weak acid with the burette to the beaker with the strong base. And this is just like the graph for that. So uh, this is how I organized it. This, oops, this left column here is talking about titrations when titrations for strong acids with the strong base. And this column on the right is talking about a titration with a weak acid with the strong base. Just to let you know. So for strong acids with a strong base, at equivalent at equal at equivalence point, pH is equal to 7, so it's neutral. And at equivalence point for weak acids with a strong base, pH is larger than 7, so it's more basic. And what's special about weak acids with a strong base? You probably remember that buffers are a weak acid with the conjugate weak base. And since we're using a weak acid as reactants, we form a buffer when we titrate weak acid with a strong base. So just know that there's a buffer for this. And because a weak base is being produced, the resulting solution is more basic. So that's why pH is larger than 7. Where on this side, strong acids with a strong base make strong acids with a strong base make neutral salt and neutral water. So it doesn't affect the pH of the reactants. That's just for you to know. You probably don't need to memorize that. Just know that equivalence point for weak acid with a strong base is larger than 7, and a buffer is involved for weak acids with a strong base. So in his lectures, he went over 3 types of questions. So 1 type, 2 type, 3 type. So I'll be going over that. So for this type of question, what's the initial pH of an acid-base titration between that's added and that? Because it's asking for initial, you can't ignore this because it's later added. So just so you're measuring the pH of this only. And to find the pH of this, you just take the molarity. You just do the pH formula, negative log for the molarity point 1 for HCl. So this is how you find initial pH for strong acids with a strong base. And I don't think you can use like reasoning to just look at a random question and see what equation you should use. So I would just memorize that if you're asked for initial pH of a strong acid with a strong base, then use this formula. Now for if the same thing is asked for the initial pH, but now it's asking for a weak acid, then you need to do ice tables. And I put the formulas here, or not the formulas, but the process here. It's the same exact way of doing as the ice tables we did before. Same exact, you can use the same exact steps. So yeah, and I'm not gonna go over it because it's the same thing, but I put it here so you can look at them if you want. But I doubt he's gonna test us ice tables for weak acid with strong base, and he's probably just gonna test us on ice tables for this part, on this part. So that's what you do for weak acids with a strong base. Now here's a different style questions where you are offered, or you're given the molarity and volume for 2 different solutions. So you have you're given 2 molarities and 2 volumes, and it asks you to determine the pH of the acid base titration between these two. So what you do is I wrote steps here. So follow these steps. So first you calculate the moles of both the reactants. Moles, well, molarity is equal to moles over liters, right? So moles is equal to molarity times liters. So, and we need liters, remember, for calculations for this, use L for volume. So we need to convert 25 ml and 10 ml to liters. Which is equal to that. And I did the same thing for moles for NaOH. Now I should break chemical. Now we write the chemical equation, which is that we have HCl and NaOH, and remember neutralization. This is a neutralization reaction, so it forms water and a salt. So water and a salt. And now third step, we identify the limiting reactant. So we know that there are, just look at that first. We know there are that amount of moles for HCl and that amount of moles for NaOH. So what would be the limiting reactant? Limiting reactant is this, it's this one with the smaller amount of moles. So NaOH would be the limiting reactant. And you subtract the limiting reactant to from both of these. So you minus that from both of these. And then you get that amount of moles remaining for HCl. And next step, again, just ask yourself if you're going to find pH or POH. So this will be acid. So you'll be finding pH. So you'll be using the pH formula, which is the fifth step. So pH formula would be this. And remember that pH formula uses the molarity of something. And what we have here is moles. So that can be rewritten as that. Yep. So what we have here is moles, and molarity is moles over liters. So, and our liters here is, we use the total amount of liters. So we use 25 plus 10 ml, which is 35 milliliters, which is that liters, and it's which is equal to m, and you take the negative log of that, which will be like that. So this is how you do, these 5 steps is how you do the calculation for strong acids with a strong base. Now for calculations for weak acid with the strong base, it's kind of similar. The first 3 steps are pretty similar. You again calculate the moles for both the reactants. So you get moles of both the reactants and write the chemical equation, and then identify the limiting reactant again and subtract that from that. The only difference, the difference here is that, remember how I said a buffer will be kind of formed? So you do the same thing of subtracting both sides with that, but then you add the amount of limiting reactant here. And then the next different thing is, instead of doing this to find pH, you use the Henderson-Hasselbalch. This equation. So it will be, so pH will be equal to pKa, which is given. I forgot to put that's given here. The pKa, which is given, so that plus, wait, pKa, so it's the negative log of that. I think it's also written here. pKa is the negative log of Ka, the negative log of that, plus the log of the conjugate base over the weak acid. So conjugate base would be F minus over the weak acid. So it's F over HF. So it's, the F value is that over, that over that. So basically get this. So, and then you can calculate it. So this is how you find pH for weak acids with the strong base. Now for the last type of questions. But before that, I said in these type of questions, we'll know the concentration for concentrated end volumes for both acid and the base. So if we see two concentrations and two volumes, we know to do this thing, and we know to not do this thing over here, which kind of looks similar. A mole and volume is offered, but and a Ka constant Ka is also given, but you know to do what's taught here because there's four things offered. So now for the third type of question that can be asked for acid-base titrations is about equivalence point. So in an acid-base titration between a 0.4 molarity, 40 mole, and that, what volume of NaOH needs to be added to reach the equivalence point? To do this, it's easier. You just use the formula, or you just use the definition for equivalence point, which is the moles of acid equals the moles of base. So if it asks for equivalence point, put the moles of acid equals the moles of base. And you have the you have one you have the molarity of both solutions, but only the volume for one. So and remember, mole equals to molarity times liters. So it's mole, just written in another way than this, molarity times liters equals a molarity times liters. Molarity times liters of this equals to molarity times meters of this. Liters of this. So it'll be a 0.4 times, again, convert the milliliters to liters. Yeah, equals to 0.2 molarity times L. So, and then that's just that, and then you can find L. That's how you find L for this. And for if it asks for a weak acid with a strong base, in these type of questions, you do the same thing of equaling that and then plugging in all the values. And I guess one last thing about this, how do you know if it's a strong acid with a strong base or if it's a weak acid with a strong base? Again, look at the acid. Is it a strong acid or is it a weak acid? And then how do you know that? From the list we had a while ago. So HCl is a strong acid and HF isn't here, so it's a weak acid. Okay, last thing for this chapter is on indicators. Just some definitions. An indicator is a weak acid that has its conjugate base a different color. And the end point of an indicator is a pH where the indicator changes color. I think it would be easier to explain this through an example. So in Gen Chem 1 titration lab, we had something like this, right? We had the burette and the beaker with the base, and actually in the burette we have the base, and in the beaker we have the acid with our indicator that indicates pink, and that indicator is called pheno something. Let's just call it pheno. Or let's just call it pheno. It's the indicator we use for the titration lab. And this indicator changes color when a specific pH is reached. So when the indicator is a specific pH, it changes color. And we use indicators because when if there's no indicator, if there's no indicator, for example, when the solution in here reaches a certain pH we won't be able to tell. But if we choose and if we choose an indicator that changes color at the pH of the solution when we wanted it to be, then we know that when it changes color, the pH of the solution also reached a pH that we wanted to. Don't worry, I'll say that another way. So in the experiment, we have the base in, we have the acid in here, right? And we want to add the base into it until it reaches equivalence point, until the amount of moles of acid equals the amount of moles of base. So we keep adding the base, to the acid, and we want to add it until the equivalence point, which for this solution is like it's like 8.8 or something like that. So we want to add the base to the acid until we reach equivalence point, until we reach it to a point where the pH is 8.8. But we don't know when the pH will be 8.8. So we use a indicator called pheno something that changes color when the pH is around 8.8. So you probably remember at the beginning it's invisible, right? Or see-through, it's transparent. And once it changes to pink, once it changes to pink, we know. Oh yeah. Also, this pheno indicator changes color at around 8.5 pH. So we know once it changes color, it means that the acid in here has added has been has its pH increased to a more basic solution from the base being dropped to a pH of 8.5. And once it reaches that 8.5, once it changes color, we know that pH has reached 8.5. So we know it has reached 8.8, around 8.8 pH. So we know the equivalence point for the solution has been reached. I hope that makes sense. And we choose an indicator that has a pH that has the endpoint where it changes color around the pH. So we choose an indicator where the endpoint is close to the equivalence point. So once it reaches that endpoint, once it changes color, we know the equivalence point has been reached. And so if we choose an indicator where it changes color at, let's say, 4.0 pH, so at this endpoint it changes color, then if it changes color, we're so far from this pH, so it will not be a good indicator for a solution with the equivalence point 8.8. I hope that makes sense. So this, if we choose the right indicator, this is how indicators help us determine a equivalence point. So a question on the exam could ask an indicator where it changes color, an indicator with the endpoint at 4.0 pH, and an indicator with its endpoint at 8.5 pH. And it can ask you, if we were to determine a solution with the equivalence point at 8.8 pH, a pH of 8.8, then which which out of the two indicators should we use to determine that equivalence point? So this chart is just uh so this is the equivalence point. It's when moles of acid equals moles of base, so the pH changes drastically, changes a lot as volume is added. And in this equivalence point, we just need kind of like an equivalence line, actually. In this equivalence line, this section, we need an indicator that falls in this section, or an indicator that changes color in this section. So if we had, out of these three indicators, which one would be the worst indicator to use to determine the equivalence point? It would be this red one in the bottom, because it barely falls on the equivalence line right here. So hopefully that makes sense. So that's all for chapter 5. What I like to do, because what I like to do is have a version of notes and a version of a cheat sheet. So two docs, basically, two Google Docs. And I do this because there's a lot of stuff here that I already understand, that I already know, that I don't need to memorize or focus on. But I must still need to skim through them. So I make a cheat sheet. It's basically just keeping what I think I should still know, what I should still keep, and I delete what I already know. So for the example, this I think I already know. And these equations, it's on the equation sheet. I know all this already. I know this relationship. I know all of this. I know this relationship as well, where I can figure it out. These, I don't know these yet. I haven't memorized them. I know acids and acids go through a one direction chemical equation, and or chemical reaction, and weak acids and bases go through equilibrium. This I also keep, but I'll only keep part of it because I just a calculation, so I already know, because I already know the other one. And same thing with this. I know to use, where I know I can use this equation and this equation. So I can delete all this, only keeping what I think I should still know. Oops. And same thing with, I know I can derive these from over here. Maybe I'll keep that strong acid base don't have an effect. Weak acid base would change pH. Maybe I'll just keep that instead of keeping all of this. I know this as well. And the steps is stable. Remember, before I decide if I should use it as stable, I decide if I see if it's a strong acid and base, or if it's a strong acid or base, or if it's a weak acid or base question. And we know that one way to know that is from the equilibrium. If it's a one-way direction or equilibrium reaction. And another way is in weak acid. In these type of questions, K will be offered, or K will be given, like in this question, K will be given. So we know it's a weak acid or base. So maybe I'll write the equation with water as reactant. Is there a anion cation? Do we use, I keep these questions maybe? Keep these two questions. And then I keep this and that. And maybe I'm familiar enough with the as tables, I delete all of this. Remember, I still have a copy here, so basically I keep doing this in a so I deleted everything I already know for the rest of the notes. I kept this as a reminder that as as the steps goes down, the K gets weaker. Uh, I only kept this as buffer because I already understood everything else. I kept this because I haven't memorized it, and I kept the most important stuff basically, and deleted the things I already understood. And for these, I only kept the steps, and then only using this 1.5 page of information, I work on all the PLTR questions, and I uh do the practice exam only using these 2 pages of my cheat sheet. And if I'm able to do all or most of the PLTO questions, or most of the practice exam questions, only using these 2 pages, that means that before the exam, I only need to memorize these 2, or this 1.5 page of stuff to do good on the exam. So before the exam, I just worry about this. I don't look at all this. If I look at all this before the exam, I'll spend time going over stuff that I already understood and not knowing what I still need to memorize because there's so much stuff. So one more time, like if I'm able to only if I'm able to do the PLTO questions and practice exam questions only using this 1.5 pages, then if I only memorize this 1.5 pages, I'll be good on the exam. That's how I do it. So I would recommend you do the PLTO not do or I would recommend you to create a cheat sheet yourself of what you already deleting what you already know, what you already understand, and only keeping the key stuff, like the steps for the ice tables, or steps for this, and then doing the PLTO questions and the practice only using this, and then uh, understanding the ones you missed, the questions you missed, which are probably just a few, honestly. Like for last exam, or for the first and second exam, I did the same thing, created a cheat sheet, and I only missed like 2 questions out of, or 2 or 3 questions out of all the PLTO and practice exams. So, I mean, I haven't done the PLTO questions and practice exam for this, but the same thing will probably happen. So that's it for chapter 5. If you want, and if this uh study guide helped a lot, or let's say you got a much better grade on the exam because of this, and you like uh here's my cash app, but Alden Chen, but it's up to you because I know the video is pretty late. So, yep, see you.